folks, welcome back to Physics with Captain Rod, making this video here to help you out with number 17 in chapter 22 of your OER college physics text. So the problem mentions something about a velocity selector, and here's kind of the idea here. All right, imagine we have two plates, one positively charged, one negatively charged, and what that's going to do is create an electric field which would be uniform and to the left. So if we have some particle that comes flying through here, like a proton, and I think that's probably what it mentions here. Actually, it doesn't, so I'm just going to assume some positive charged particle with a velocity vector this way. Now, if we draw a free body of this, I'm going to draw that right here, right? The Coulomb force acting on it is going to equal charge of this object times the electric field strength, and that's going to be to the left. Okay, so we're going to get that force equals whatever the charge of this particle is times whatever the field strength is. Now, if no other forces were acting on this particle, it would crash and burn over here somewhere. The idea between a velocity selector is to superimpose another type of field, in this case a magnetic field, in such a way that the magnetic force on this particle is to the right. So that's going to be a magnetic force instead of a Coulomb force, so that this particle could then move on with constant velocity. Right? So first of all, let's talk about the field direction. In order to get a force to the right, and you should confirm this by right-hand rule, the magnetic fields would have to be this way, or in the what I would call generally the plus K direction. So there's an example of a B field. So if you're watching this video, make sure this is clear. Right hand fingers parallel to the velocity. Rotate till you can sweep this way, or in other words, point your palm in the plus K direction, and the magnetic force would be to the right. Now, the magnetic force is equal to QVB sine of the angle between the V and the B. So in this orientation, like so, this would generally be a right angle type of problem. This is going to be a 1. So write an equation that sets the net force equal to 0, and that will allow you to find the electric field fairly easily. And once you find the electric field, let's see, that's the answer to part A. Part B says what voltage between the plates do you need. So these plates are separated by a certain distance, let's say D, and remember field potential difference is field strength times distance. Sorry about that crummy E. So once you get an electric field, you can pop that here to calculate the potential difference between the plates. So again, let me go back and just overview this idea of the velocity selector here. So you have an electric field superimposed with a magnetic field. And the big deal here is that the magnetic force is velocity dependent. So with the electric field to the left, the Coulomb force would be to the left. With the magnetic field in the plus K, like I have it, the magnetic force would be in the plus I. And that thing is speed dependent. So what happens is if the particle comes through here too fast, this force will be bigger and the particle will crash on the right somewhere. If the particle comes in too slow, the magnetic force isn't big enough, particle crashes over here somewhere. But like Goldilocks and the Three Bears, if the particle comes in at just the right velocity, it can go straight, undeflected. So that's the idea between a velocity selector. And keep in mind that the electric field here is really easy to manipulate via the charges here. So you can basically push more charge onto this, gives you a stronger field. So you can set this thing up to allow any velocity that you want to pass through it. So that should be plenty to get number 17 done. If that helps, have a great day.